In this lecture, I'm going to describe underlying hardware resources that the operating system must manage in order to share the computer system among multiple different applications. Now, it's convenient to think of a system, a computer system, as a set of layers, where at the top layer we have a group of applications. These are the programs that we run and with which we interact on a day-to-day basis to accomplish various tasks. These applications are built on top of libraries and utilities, some of which are included with the operating system and some of which are installed separately. Now, the operating system acts as an intermediary layer between the application layer and the utilities and the underlying hardware. The underlying hardware consists of several important pieces. I'll talk more in detail about these in a moment, but the two primary pieces that come to mind are the central processing unit, which actually executes the program instructions, and the memory hierarchy, which provides a place to store instructions and data for use in computation. Now, the memory hierarchy is critical to understand because the speeds of each level of memory within the hierarchy vary. The fastest memory consists of CPU registers and then the cache attached to the CPU itself, whereas the slowest memory consists of persistent memory, typically disk. Now, hardware also includes a bunch of input-output devices. We have a keyboard, mouse, network interface card, a screen, printer, plenty of others, webcam, different types of devices. One of the other things that the hardware does is supplies power to the system via power supply and removes heat generated by the system through cooling. This is typically done through fans built into the computer's case. Now, when we look at a computer system from the outside, we see something called a form factor. A form factor is simply a set of specifications for standard sizes of equipment to allow different computer components developed by different people to be interchanged with one another. And standard form factors include ATX, which is a typical workstation size form factor, micro ATX and mini ITX, which are used in small form factor systems such as bookshelf systems and home theater PCs, and rack mount systems, which are typical servers in a data center. Now, laptop systems are a special case. These types of systems typically are proprietary in nature to the extent that it's not easy to take components out of one laptop and put it in another laptop. Workstation systems, however, do allow easy component interchange. And these are the simplest of systems. They typically support multiple users, but normally only one user at a time. When a workstation is shared between different users, it often involves a user getting up from the keyboard and another user sitting down. Of course, it's not always the case, but generally that's the case. Workstation systems are also frequently either ATX or micro ATX form factors, and each workstation typically has its own power supply, which can be an issue of efficiency considering the power supplies are only about 65 to 85% efficient. Workstations can be used to host server applications. This is particularly true in smaller settings such as small businesses, nonprofit organizations. Server applications in larger scale environments such as enterprise environments are typically hosted in rack mount systems. And rack mount systems are simply a space-efficient way to put a whole lot of servers into one data center. Rack mount systems are measured, or rack sizes are measured, in terms of units, or U, and a typical rack's 42 U tall. So the most space-efficient of servers, a 1U system, with 12 cores in each machine, could enable up to 480 cores, 480 CPU cores to be supported by a single rack. However, there won't be much room for expansion. There won't be much room for extra devices or extra hard drives. For that setup, we use 2U and 4U systems, which are less space efficient, but do allow for more expansion, more disks to be included, and more add-in cards. Now, if we take a computer system and we open up the case, inside we're going to find a power supply, we're going to find a motherboard, or what Apple calls a logic board, and attached to that motherboard we're going to find the CPU, we're going to find random access memory, we're going to find expansion slots for add-in devices, some of which may be populated, and we're going to find that the motherboard contains its own onboard devices, such as network controllers or video controllers. Inside the case, we're also going to find persistent storage devices, such as hard disks, solid-state drives, and optical drives. And here's a conceptual view of what the inside of a computer system looks like. Here we have the motherboard, which has some expansion slots. These are normally used for add-in cards to be plugged in to add functionality to the system. Onboard devices, which are soldered onto the motherboard and are not removable. One or more CPUs, which are typically removable. These are typically separate chips. And each of these chips inside, you can't see them, but inside are typically multiple CPU cores and some kind of cache memory. Random access memory is another type of memory that's attached directly to the motherboard, and it's typically in the form of removable modules. Connected to the motherboard via cables, we find a hard disk, optical drive, perhaps a solid-state drive. Now, the central processing unit is the part of the computer that actually executes the instructions. It has one or more execution cores. Most modern CPUs have at least 2 cores. CPU registers are used for direct computation, direct operations that are occurring right now. The cache is used to store program instructions and data that will be used immediately, the next few instructions that are going to be executed. This cache is divided into levels of different speeds. It's also volatile. It loses its contents whenever power is disconnected. And it's expensive. This type of fast memory is quite expensive. Now, random access memory is separate from the CPU. This is used to store programs and data while the program is in a state of execution. This memory is several orders of magnitude faster than hard disks or even solid-state drives, which is why programs are loaded into random access memory by the loader before they start executing. Most programs also buffer their data in RAM for speed. However, the memory in RAM is still volatile. The contents are lost whenever power is disconnected, and it is more expensive per unit storage than disk space or even solid-state drive space. Persistent storage is the slowest of all types of memory in the system. This is non-volatile storage for data that's to be saved whenever the system is powered off. Now, this is the least expensive type of storage per unit of capacity, but it is slow. It's not fast enough to execute programs directly, largely because the CPU would constantly be waiting on the drive to give it the next instruction, and that would slow down the CPU. Hard disk drives are what we typically think of when we think of slow persistent storage. These are mechanical devices that use magnetic storage, basically a magnetic medium on top of either a glass or metal disc called a platter, and multiple platters that are stacked spin at high speed with the heads moving back and forth between tracks on the platters. Accessing data on a hard drive is thus subject to 2 types of delay: a seek time, which is the time required to move the heads back and forth, and rotational delay, which is the time required for the platter to rotate around to the location where the desired data is stored. Now, hard drives are relatively inexpensive per unit of storage space, but they are mechanical, which means they're guaranteed to fail sooner or later. Here's a diagram of a hard disk, and here we can see the platters, which are stacked on top of each other and spun around by a motor. The motor spins this around at high speeds. The head moves back and forth. Now, there's typically one head per side of each platter, so the heads are actually stacked up, and a servo motor moves the heads back and forth. The time it takes to move the head from the inside of the platter to the outside of the platter, or from the outside back to the inside to get the appropriate track on the platter where data is located, is called the seek time. The time it takes for the spot where the data is located to rotate around under the head is called the rotational delay. So if I have a piece of data right here about where the mouse pointer is, my drive is rotating clockwise, the head has to seek to the track where that data is going to be located, and I have to wait for that data to come all the way around and wind up under the head so that it can be read. This adds to delay in accessing, reading, or writing data from the hard drive. So in performance-critical situations, we'll typically use solid-state drives. These drives have no moving parts. They instead use solid-state chips to store data. Consequently, they have no seek time, no rotational delay, and faster burst transfers. Much higher performance than hard drives. However, this performance comes at a cost, and solid-state drives themselves will eventually fail. Each block of an SSD can only be written a finite number of times before it wears out. The drive itself extends its own lifetime by reallocating blocks dynamically so that each block is written an average number of times instead of a large number of times. And this process is called wear leveling. It extends the life of the device significantly. Now, given that our persistent storage devices are guaranteed to fail in time, it is critical that system administrators keep backup copies of programs and data so that the system can be restored after a failure. Now, the backup media should be stored separately from the computer center itself. Best practice is on-site, at least 10 miles away, in a location that can be protected from damage as well as theft or loss of data. Backup media include optical discs such as recordable CDs, DVDs, or Blu-ray. These optical discs are nice because they're inexpensive, however they do degrade over time. Scientists are still working on the details of exactly how long, but it is known that data will become unreadable eventually. Flash drives such as USB sticks are also inexpensive, although a bit more expensive than DVD media. They're slow, sometimes slower than DVD media, and they themselves will lose data eventually due to electrical properties inside the flash memory. Tape drives are considered best enterprise level solution, which of course means they have the highest costs, but they have the best reliability on average despite being somewhat slow to access for reading and writing. Cloud storage is another option for many users, and in this model, backups are simply uploaded to a remote server that someone else maintains. This is typically a backup service provider. Cloud storage is relatively low cost and convenient. However, its speed does depend upon the internet connection that you're using to send data to or retrieve data from the backup service. And theft of data can be a concern. So, the operating system implements a common mechanism for allowing applications to access and share hardware. The applications can make requests from the operating system via system calls. The operating system can deliver hardware events to applications, and this is how we allow our applications to make use of the underlying hardware of the computer system.